we switch over to the other math and healthcare hubs, really very much looking forward to hearing from them as well.
Thank you very much, Carola and John, for inviting us to come here and present at this event. So, hi everyone. My name's Nicholas Ovenden. I'm a professor of applied mathematics at UCL, and I'm here to introduce Chimera, which is an EPSRC-funded mathematical sciences and healthcare hub. And Chimera stands for Collaborative Healthcare Innovation through Mathematics, Engineering, and Artificial Intelligence. Oh, let me see where I got that. Okay, so let me tell you about the focus of Chimera is pretty much in terms of critically ill patients. So we're focusing very much on the intensive care unit. So I'm sure everybody's aware of this, particularly with the pandemic, how important ICU beds are and ICU support for some patients. So patients who undergo respiratory failure, need ICU beds, mechanical ventilation to keep them going whilst their lungs heal, the inflammation goes down, etc. And this is a very expensive resource and a vital resource sort of in the NHS to allocate wisely and to use effectively. It's worth noting that there's 100,000 ICU admissions in the UK per year, typically on an average year. And the average daily cost of each ICU bed is about £1,500. And it was noted in a study, probably about in 2003, I think, where there was significant human errors on ICU. So there's a quote of 1.7 human errors per patient per day. And of course, as you would expect in ICU, there is a very high mortality rate. So our interest, is using mechanistic models to model these patients. And why is that the case? Some important aspects that we've got here is it's very difficult to conduct research on critically ill patients for a variety of reasons, including fragility, ethics approval, etc. And so there's a lot of issues around doing experiments, extremely difficult to design, highly expensive, small sample sizes, etc. When you try and study the physiology, there's no real single animal model that typically replicates the lung very well. It's quite difficult to look inside the lung, as I'm sure if you're involved in medical imaging, you know, and to understand what's going on. In the meantime, though, there's a demand for getting more personalized treatment strategies, because every patient on ICU often has a unique set of circumstances. And there's very much a strong interest from the funding agents and industry. So yes, as I said, a lot of this physiological knowledge we've had is from decades ago, often using animal experiments, which probably wouldn't be ethically acceptable nowadays, or a lot of experimental data from lung function comes from cohorts of samples of young, healthy adult males who don't typically represent the kind of patients you find on an ICU ward. And what we've got to do, though, is try and interpret this physiology and this understanding in a very complex environment of an intensive care unit. And one of the sort of what kind of the motivation which started this the formation of this hub is our collaborators at UCLH, University College Hospital, and Great Ormond Street Hospital. They now are producing a huge amount of data from their ICU patients. A large amount, this T3 etometry platform, and this is sort of data every 5 seconds on all sorts of things, because of course these patients are extremely heavily monitored. That's one advantage in terms from the modeling perspective. But of course, a lot of this data simply gets binned, or the vast majority of it, and only a fraction of it is used to make any kind of informed treatment decision. There's also, of course, with the data, there's a lot of artifacts, issues when suddenly something happens to the patient, like they're repositioned or there's a line is taken out and cleaned. These aren't necessarily recorded at the same time as the electronic data is coming in. So there's a lot of artifacts and details of the data. The data has to be cleaned up. So what's our aim for Chimera? Well, we really want to use the real patient data, and we want to combine the innovations in data science, biomechanical modeling, and advanced machine learning techniques to kind of uncover these hidden signals and try and develop an understanding of the patient's physiology whilst they're on an ICU bed, and their sort of journey from illness to recovery, hopefully. And of course, Chimera aims to become a well internationally recognized hub focused on treatment of critically ill patients. I mean, some of the challenges that the clinicians face on a day-to-day basis is when do you extubate someone? When do you take them off a ventilator? Because obviously, if you leave them on too long, there are aspects of if you're on a mechanical ventilator and you're using positive airway, you're blowing the lungs up. That causes lung damage if you leave people on it for too long. It also costs an enormous amount of money to keep people on longer than they need to. However, if you take them off the ventilator too early, they may go through a lot of trauma because it's been taken off too early, and then they have to be intubated again, and that's not something that you want to have to do to the patient. So you want to find the right time. So that's a typical example of a challenge that, amongst many others, that are faced on ICU. So let me give a few details about Chimera. So the program is divided into, it's a four-year grant, exactly like the Cambridge Hub, and the work is divided into these 6 work packages. Work package 1 is statistical learning from the clinical data. Work package 2 is when we're looking at testing and improving the biomechanical models, and work package 3 is the advanced machine learning, trying to learn the underlying model structure using some neural network techniques. And then those are the principal work packages, and then the sort of supporting work packages beyond this is work package 4 is basically engaging other academics and other clinicians. Work package 5 is very important. That's about getting the data in the right form, building the infrastructure so other people can access the data and we can access the data, sort of automating various tasks in the data. And then work package 6 is, of course, patient and public engagement. And I'm afraid it's probably a bit small, but these details are on the website. This is just that I will acknowledge people. I have acknowledgement pages, but just to give you an idea of the structure. So we have 4 partners. It's UCL, the Turing Institute, and the 2 hospitals, UCLH and Great Ormond Street. And then we have 2 directors, Professor Christina Pargel, who's in CORU, the Clinical Operations Research Unit at UCL, part of UCL Mathematics, and Professor Rebecca Shipley, who's in UCL Mechanical Engineering. And then we have the support team, Julie, Marilyn, and Georgina, who work with us. We also have our clinical partners. So we're very fortunate to have a professor of pediatric intensive care and a consultant in pediatric intensive care from Gosh. That's Mark Peters and Sam Ray. And then in UCLH, we have Steve Harris, consultant in intensive care. And we also have Claire Black, who works in critical care psychotherapy, physiotherapy, sorry. And it's quite important to realize that actually when ICU patients, their journey to recovering is a very long road. So once you get off ICU, it does stop. You don't leave the hospital the next day. There's a very long recovery period once you get off ICU, getting you back to hopefully to some kind of level of normality. There's also a registrar, Ed Palmer, who works with us in intensive care as well at UCLH. And then we have the work package leads, myself and Vanessa Diaz in mechanical engineering. We're in work package 2 on the biomechanical modeling side. We have Dr. Alex Diaz and Professor Gianluca Bio on the work package 1, the data science side. And then we have Professor Simon Arridge in computer science, who's leading the machine learning side. And then we have our postdocs and our PhD students. We have a postdoc in each of the work packages. So that's actually Victoria Volodina has recently started for the data science. We have Stina Safaran, who's the postdoc in work package 2, and we've got Sandip George, who's a postdoc in work package 3, and then we have two PhD students. There's Sam and Hugh for the data science. I'll show their names at the end. Manuel and Abigail working in the biomechanical models, and we've got James and Gevic working in machine learning. Okay. So progress so far. Well, we started officially in January 2021. We were fairly successful in recruiting. We've had a bit of changeover during the time with a couple of PDRAs, but overall we've recruited well. We've been having weekly meetings for a long time, since August 2020. We have a monthly seminar series established. We have a Twitter account. We've I think actually this is the old one, actually, not the one I sent, but we've developed already some new collaborations, both in UCL and externally, with Galway and Warwick, looking at positioning of patients. We did hold a data study group, but we've also been holding some new external events this year. So we just held a Turing engagement event internally last week, where we looked at a particular challenge in terms of gas exchange in the alveoli, and we're also going to run a clinical engagement event later on in 2022, establishing a data platform, etc. And we've also got ongoing discussions and developments in terms of data governance and ethics approval with both our clinical partners. So what I'll do now is, in the remainder of the talk, I'm going to go through some of the projects that are being worked on in work packages 1 to 3. I thought that's what I would go through here. So let's start with work package 1, the data science. So this is a blood gas project that Victoria is leading on, but it's in combination with Alex Diaz, the Sam Ray at Great Ormond Street, and Jim Smith at Warwick. And they are trying to construct a dynamic Bayesian network to look at the oxygen affinity state. So this P50 measure, this P50 measure is the partial pressure you need to achieve a 50% saturation of hemoglobin, which is a crucial factor in ICU. And how they're approaching it is they're looking at various control factors. So they've identified lactate pH and partial pressure of CO2. And they've got this graph to analyze how the sort of causal relationships between these various aspects. And one of the important things about this project is how they treat the uncertainty of the measurements. So they're propagating the uncertainty over these control factors so they can understand the uncertainty in the predictions of the oxygen affinity state. And well, this is just some of the details, but I'm sure if you're interested, you can contact Victoria or Alex about it. But you identify these various clinical variables. So we've got 4 there, which are the ones I've just highlighted: lactate, pH, PCO2, and the P50 that we want to measure. You have a set of parent variables, and then you decompose the whole network. And then they use this dynamic linear modeling sort of time series, using a sort of regression model for time series, to develop a short-term forecast. And that's what they're doing at the moment. And then the current plans that they've got is, now they've got that going, is their future work is to try and incorporate further information about medical treatment when interventions happen and how that affects the P50 signal. So perhaps doing that when it's actually recorded to start with. And then what they want to do is, if there is a medical treatment, but there is actually information not available, can they spot what medical treatment is happening in the data? And so they can sort of highlight these events automatically. And then, of course, the goal is to try and improve the P50 values in these ICU patients. So that involves specifying an inverse problem of a Bayesian type, so that they can optimize that value for these critically ill patients in terms of how you control these various factors. So that's one of the things that's going on in work package 1. Now let me move on to work package 2. And so firstly, I'll talk about One of the things we've been looking at is patient position, which I'm sure is once again something that perhaps you didn't consider in the past, but was talked about a lot during the pandemic. This idea that positioning patients, lying them on their front, so in so-called prone position, seemed to be a very useful strategy with COVID patients. But of course, there's a lot more to it than that. I mean, how long, when do you do it? How often do you turn them? It seems that there's a certain time frame that they need to recover in that position, and they can't be in that position for the whole duration. So they have to be constantly moved. So of course, Abby, who's a PhD student, has been looking at this and started initially with looking at various, using a sort of solid mechanics approach, looking at deformation of the lung under its own weight in various positions. We took the example because very often, one of the things to make a point here with Chimera is we're not looking at fully complex 3D models. We're trying to look for an adequately complex model for a critically ill patient. So we're not going to have all the we won't necessarily have lung scans for these patients. You really want to try and fit the parameters to the data that's available. So obviously one of the initial models that people look, simple model of the lung that people look at is a sort of cone missing the apex, as it were. So to start with, looking at truncated cone and how it deforms in different positioning. It turns out that this involves some nonlinear effects, that the elastance changes depending on the positioning as well. And what we're interested in is this regional ratio between ventilation and perfusion. So this is about how much are the alveoli in that part of the lung, how ventilated they are, how much oxygen, how much gas exchange is being able to take place. And then on the other hand, how well they are perfused, because the blood, there's gravitational effects with the blood in the pulmonary system. And of course, if you have well ventilated but not perfused alveoli, that's not very useful. That's a sort of dead face. If you have a well perfused alveoli with no ventilation, then that's also not very effective. So you're trying to get these typical VQ ratio approaching 0.81, and this just shows, according to the lung height in different positions, how that relative ventilation perfusion ratio, how those ratios and the ventilation and perfusion change according to height in different configurations. And then, of course, we've looked at other specific geometries and elastic models. So that's one aspect we're looking at the moment. A second aspect, this is what Manuel has been looking at, is this sort of ICU twin. So looking at a cardiorespiratory model that's going to sort of, in a sense, mimic side by side with the patient. So you want the sort of software being used at the bedside, a mathematical model you kind of bolt onto and sort of reduce, plug and play, and various increase or decrease complexity, as it were, and to be able to model the effects of various treatments, and generally be able to monitor the evolution of the patient's stay and try to estimate parameters in real time. One of the main aspects of this, there's a cardiovascular model, but I just decided to focus on the lung model. So this is where, with a few parameters, you can construct a fairly rudimentary model of the lung by specifying various things in terms of resistances, compliances, angles of branches, etc. You can sort of build a tree, and then you can then look at the pressures on the alveoli and also couple it to a cardiovascular model and simulate things like the sort of control responses, the sort of regulatory responses developed by sort of baroreceptors, etc., how the body's controlling it, because that's something, trying to keep how the critically ill patient may remain stable or become unstable over time. And this is just some of the preliminary results, some of the plots you get. Obviously, this is where you connect it to a ventilator, and then you have a ventilator in either pressure control, where it's deciding on what the airway pressure is going to be, or volume control, where it's deciding how much tidal volume we're going to put into that patient over the course of the breathing cycle. And this leads to a third project in the biomechanical, which is what Sina, the postdoc, is working on. We're very interested on the pediatric side in this so-called high frequency oscillatory ventilation, or HFOV for short. So this is a technique, it's a lung protective strategy. It's kind of used when conventional ventilation fails to work any longer. And what you do is, instead of having this blowing up the lung using a positive pressure and deflating it, because these lungs are extremely damaged in these pediatric patients, you mildly inflate it at a mean air pressure, and then you just have a fluttering small tidal pressure, fluttering about 10 hertz or 8 hertz or so. It doesn't seem to work in adult patients, so it's not used. It's used in pediatric patients very much if conventional ventilation isn't working. And the idea, of course, is to tweak the various settings, which clinicians do using experience and guidelines in terms of monitoring blood gases, to make sure that the patient is adequately ventilated. But we wanted to understand a little bit better about how this works and convert a model that we already have of the lung to be able to understand this high frequency system. One of the so you have this highly oscillatory pressure. Of course, the inspiration expiration, even at the high frequency, is not they're not symmetric. So IE ratio is typically 1 to 2, which means it's a third of the cycle you're breathing in, 2/3 of the cycle you're breathing out, and that's even the case at high frequency. It is very interesting because of these small tidal volumes. So the in conventional ventilation, the tidal volume, you basically push a plug of air all the way through the branches to the alveoli. But this oscillatory effect is quite small. It's only about 16 milliliters going in and out. And of course, pediatric lungs are quite small as well. But we're trying to understand how that frequency, etc., and that control of tidal volume improves, or how we can optimize ventilation of that patient. And I'll move on now to work package 3, which is the advanced machine learning techniques. So this is some work on predicting the outcome of extubation. So I mentioned about the fact that you want to know, if you're going to remove someone off a ventilator, how stable are they going to need intubating again, or are they going to remain stable when they're taken off the ventilator? And so what Sandip has done here is looked at a variety of complexity measures. So they've got some time series data that you would expect, sort of heart rate, respiratory rate, blood pressure, but then they're looking at some nonlinear measures of those time series data, like fractal dimension, entropy, various interactions, this mutual information. And then they're trying to see if, including these complex measures, they can somehow predict the outcome. So you're basically seeing if these nonlinear measures differ between individuals who either failed to be extubated or not. They had data 24 hours before removal of the tube, of the endotracheal tube, and they looked at the success rate of that. And then, I mean, in a sense, though, they looked at these various models with the complex measures and without the complex measures, and looked at the AUC. I mean, the result was, in a sense, is that they got a marginal improvement in the AUC when they added the complex measures. So, meaning that you're getting a better true positive rate, as it were. You're making a better prediction than just random, which of course is the red line. The idea now is to perhaps work with the data science group and see how we can improve these things a bit further. And then, as I want to move on, I've got just one more quick project to mention, and that's being done by Gevik. These are these grey box models. So one of the things we really want to work together with the data, with the machine learning and the biomechanical model is, the modelers are very used to sort of white box models, so-called, or where you have a deterministic system, some system of ODEs, or coupled with PDEs, that you have some parameters to fit. But these grey box models, the idea behind this is that you have some uncertainty about what terms should be in that system of ODEs. So you're not sure if it's like the adding or taking away various components you think possibly are negligible, not very important, or perhaps they're dominant. And the idea behind this is to use neural networks to try and fill in the gaps to see if there are things missing in the systems of equations, and then to try and use it as a tool for long-term prediction. And so the idea behind this sort of universal differential equations is you have an incomplete mathematical model that you're using, which isn't fitting the data. Try and replace them on the unknown parts with neural networks. That creates a gray box model. Train that model using data that you have available, and then see if you can learn what terms are missing. So what Gevic did initially, of course, is try to work on a model that kind of fairly well established these Lorentz equations, which you can get some nice dynamic behavior of. So the original model is up there, where you've got these extra terms here in those, this minus y in the middle one, and the minus 8/3 z in that one. And you try and do an untrained prediction. You don't get a very good fit between the ground truth, which are the dots, and the predictions, which are the lines. The gray box model, you develop neural networks where you put these sort of various weighted certain terms in, and you can learn and then you attempt to learn what terms are missing to fit the data. So I think I've just got a couple of slides left. I think it's important to emphasize with Chimera that there's a lot of importance in terms of, we've got data science, biomechanical models, and machine learning techniques in these three work packages, but it's very important that we try and bring those together. That's where the novelty is going to come in terms of this project. So here's just some examples of what we're doing in terms of interacting with the work packages, just sort of referring to that. So between data science and biomechanical models, been looking at using emulators and using history matching to improve the performance of fitting all these parameters. So an emulator which is running a lot faster than the sort of full model. I've just mentioned the gray box approach, and that's how the work package 2, the biomechanical models, are working with the advanced machine learning team, trying to set up a model, but then maybe try and see if there are terms missing when we try and fit the data, rather than just doing a simple parameter fitting. And with the data science and machine learning, one example is what I said with the predicting the extubation outcome. So using some combination of data science and the machine learning techniques on the time series data to try and improve that that predictive rate, looking at the data. Okay, and I think I'm just come to the end. So I just want to acknowledge, here's a list of, I mean, I'm very grateful to all the colleagues who've helped me and put this presentation together, particularly Victoria and Alex for the blood gases, Sina, Abby, and Manuel for all the work package 2 stuff, Sandip and Gevic who supplied details for the machine learning examples. And what I just wanted to say is, if anybody here is interested in this work and is interested in collaborating with us, we would welcome you to contact us. We're planning various events going forward, so please come to UCL, attend one of our events, and let us know if you're interested. Thank you very much.
Thank you so much. That was really great. Thank you. Very interesting. I think we have time for a couple of questions. Don't run away, Nick. Okay. Other questions? Okay, please go ahead.
Okay. Yeah. That's something definitely. Thank you for that. I will refer that to the practice for it.
I had a question, Nick, about well, specifically about the gray box models, but more generally, maybe because a reoccurring theme, also something that we are very interested in the CMIH, is this combination between data-driven approaches and first principle models, right? So mathematical physics-based models. And always the question, that you start off with is how do you combine the two in the best way, right? You can start with one and then try to fit in the other, or the other way around, right? You could start with a neural network and then try to put some structure in the neural network to make it more like a physical model. So in the gray box models, you did it the other way around. You started with a PDE and then put in the neural network for the terms you weren't sure about.
Yeah.
Or you thought are probably the regions where there was a bit of an inaccuracy in the model. How interpretable? So the one question is, what is your general approach? Is this your general approach, or can you see also situations where you start with a neural network and then put in structure in that? And then the second question is, how interpretable are these additional terms still that you put in?
I think that's a good point. I mean, so what I would say is, I think our current approach, although the one that we're tackling first, is this idea that there are a variety of models out there of various complexities that we can adopt, for instance, for the respiratory system. But what we want to know is how do we can't model everything, so we need to knock out certain things. So we want to develop. So I think the way we want to approach it is start from a fairly simplistic model and then try and build up and use the machine learning to help us
make it more accurate.
Building process to reach the right sort of level of complexity where we can feel we can model these spaces. That's where I think our approach is. I think the other approach is equally valid, but I think that's the way I see it from our side. But of course, it might be interesting to look at the other approach and see if we we can almost sort of try and meet somewhere in the middle. And I think the way that we're trying to assess that is if they do so I guess there's a guiding principle here that you can offer the neural network some ideas for extra terms. So you can provide it with a template of something that is physically relevant and maybe knock out terms which you can't possibly pin onto a particular physical mechanism, but you can also let it run a little bit loose and see where it goes, and then throw that back to the biomechanical models to try and sort out why that process might occur. So I think it's a little bit of a two-way thing. That's very much at the forefront of what we're doing.
Yeah.
So I think it'd be useful to report back on that over time.
Yeah, it's very interesting. Thank you so much, Nick.
Yeah.
Thanks a lot. Ciao. Quick question, Ciao.
Sorry. Just I'm wondering, include the digital chain, have you considered like the ventilation mode or any patients or any interactions of this? Because I think it could significantly impact the pathophysiology of the patient.
So you mean in terms of the mode of the ventilator on? So you mean like the pressure control or volume control? Is that right?
Yeah. Also, kind of the different patients. Also, some patients may need to switch off between these different modes. It's very dynamic.
I think I would say that's not something there's something we're aware of, but it's not something that is currently our focus. But that is an interesting idea going forward, to think about what setting people should be on. So it's a good point. But I would say at the moment our main concentration is on pressure control, which is the most common.
Yeah.
But then there are a variety of modes. But the main one is pressure control, but then volume control. But I think it'll be interesting if there was a model to kind of suggest how that interaction would change if you were to switch the settings on a ventilator. But I think at the moment that would be something that's probably developed a little bit. But it's very interesting.
Sounds like a discussion for the coffee break. Yeah. Thank you so much, Nick. Thanks a lot. So our next